Hello dear friends. In the previous lectures we have discussed about the theoretical framework of the volatility models. Today we are going to discuss the implementation of those models using the real data of the Indian financial markets. So in the previous lectures we have discussed about the multivariate GARCH models and the stochastic volatility models. In the multivariate GARCH models, we have discussed various extensions. For example, we have discussed multivariate GARCH model, the VECH, diagonal VECH, BEKK, DCC and ADCC. Where is the CC, that is the conditional correlation. So we have discussed about the multivariate GARCH models with VECH, diagonal VECH and BEKK. Then another approach we have discussed. So all these basically modeling variance and covariance. Whereas another approach we have discussed, that is the CC, which is constant conditional correlation. Then we have discussed the DCC, that is the dynamic conditional correlation. And third, we have discussed asymmetric dynamic conditional correlation. So in these three, basically we try to model directly correlation instead of covariance. And then we have also discussed about the stochastic volatility model. In this case, what we are assuming that volatility is the constant deterministic. That means in the variance equation we do not have an error term. However, in the stochastic volatility model we have the error term into the volatility or the variance equation. And we have seen that in case of multivariate GARCH model, specifically in these three approaches, what we have, the known as the concept of curse of dimensionality. So basically this is happens because of this. We have the two. One, we have the general ability. Another, we have feasibility. So if we are generalizing, you are making too general to the model, then we may not be able to estimate such parameters. Now in these three cases, what we are observing that if you are including the large number of variables, then the number of parameters to be estimated increases quadratically. So it becomes difficult to estimate such models, and often we have the problem of dimensionality, the problem of degree of freedom. Therefore, most of the time we try to directly go to the model, the correlation models. However, in the correlation models, in the first case, there is a constant conditional correlation, is quite a restrictive approach where we are assuming that the correlation among assets is not changing, which is not true in the real world. So in that sense, the DCC model extension is quite relevant, where we do assume that the correlations are not constant, it is changing. Then on the ADCC is basically assuming that positive change and negative change have the different effect on the correlation. So in this lecture, we will focus here in this model here, because all other models are similar in estimation process. There is the minor differences we have in the estimation process. So though we will be estimating this model also, however, I will be focusing on the more discussion on this model. So let us quickly go to this here. Again, the similar approach we are following, that we will have a project folder. In that project folder, we have the script file where we will be using those script file to conduct this or perform this task here. So let us first talk about the stochastic volatility model. So here we have stochastic volatility script file. Now, once we have this, then what we have, the first it is showing the message, okay, this particular package is not installed. So let us first install this package here. So once we have installed that package, now next task we have to load those here. So let us load those packages here. Then we are directly downloading the data from the internet. So we are first giving the details of the data. So defining the range from start date is where and end date is here. So start date as date. So basically we are asking this should be considered as the date format, and this should be also considered as the date format. So we are defining start date and end date, which we have stored it here. Now first we'll get the Nifty 50 data. So we are getting get symbols and a source and start from start date to end date. So let us take this. So once we have this NSE, again here we can see we have the different opening, high, close, low, close, volume and adjusted. Out of that we will be using the closing price. So we are using Nifty as the closing NSEI. So we can see Nifty now what we have, only NSI close, that is the closing price we have. Next we are taking the exchange rate data. So exchange rate data we are taking here, this exchange rate data. So you can say USD INR, this is the exchange rate closing data we have. So now the first we have downloaded those data. Now we are preparing those data for the estimation. First thing we will calculate the log return. So we are calculating the both the returns, that is Nifty returns here we have, and the exchange rate returns here we have. Then we are merging these two data to make a data frame. So combining this data, and here we have this returns data, and here we have this Nifty returns and the exchange returns. We done. Now add the date column to the merge data. So we are adding the return data here, the date column. So the changing column names here, this. So if you see here, this we have date columns. Now converting that as the XDS here. Now let us first visualize those plots. So this is the daily log return of the Nifty 50, and this is the daily log return of the exchange rate, and we have the data from January 2015 to here we have 3rd December 2020, and this is the overall view have. So these are the basically example of the volatility clustering we have at the lot of places there. Now so next what we are estimating the stochastic volatility model, which is quite straightforward. We are using the function SV sample, and we are estimating first for the Nifty return, second for the exchange rate. So we are estimating this, and here we can say that it takes this data here, this stochastic volatility model. Similarly, we are using now exchange rate. So you can observe it will be taking little time, and we will have this. So once we have estimated, now let us summarize those results here. So this is the summary of that results we have. So what we have, these are the prior distributions we have, and here the basically posterior estimations we have. So what we can see here, the mu is the mean, phi is the basically mean equation we have, and sigma and exponential sigma here and the sigma square here. So this is the basically for the variance equation we have, and this is the for mean equation we have. And we can observe here, these are the mean and this is the standard errors we have, and this. Now similarly we can summarize this. Now let us take the diagnostic test of those estimated problem here. First what we'll do, plot the ACF and so this is ACF of the residuals here and the ACF of the exchange rate here. In both cases we are looking that it is only at 1 lag here. After that it is almost 0. So that means the model seems quite good fit because we do not have more the problem of ACF and the PCF. So let us diagnose the plot the residuals here. So this is the residual we have, and from here we can observe certain aspect here. So this is the original data and this is the residual plot. So the residual plot quite clearly shows there is no more pattern. So if there is no pattern, that means there is no problem of heteroscedasticity we have. Similarly, we can say this is the plot of the original data. So the divergence from the QQ plot basically from this line is basically reflects that. So the divergence from this line basically shows there is the problem of non-normality or autocorrelation. Here we can see it is except a few points, it is everywhere perfectly fit on this data. That means this is the standard normal distribution we have. We do not have the problem of autocorrelation or the heteroscedasticity here. Now similarly we can plot the QQ plot again. So again it is showing that there is the data is normal here. Now let us use the forecasting volatility here. So we are using the predicts, we are using the model name and we are testing 10 ahead forecasting. So let us plot that here. So it's quite straight, it is showing, there is not much variation it is showing. So let us plot the latent volatility here. So if we see here now, so what we have, this is estimated volatilities at the different percentage we have. So at the 5%, 50% and 95%. So this is the estimated volatilities we have. This is the density of mu, density of phi and density of sigma. It seems quite reasonable well fit in this particular case here. Now let us visualize the estimated volatility here. So here we can say estimated volatilities is quite follows a similar kind of pattern which we have discussed, we have seen in the original data here. It seems that this model is quite good fit into our case. So that's all about the stochastic volatility model. Now let us go back to the GARCH DCC model here. So before that, let us clean here this data and also the plots. So let us. So here for the GARCH is basically final GARCH model here we have. And to estimate the multivariate GARCH model, basically we use the package RM GARCH, RU GARCH and MTS, which is not installed into the system. So therefore, first we are installing that. So once we have installed these packages, let us use the library function and attach those packages into this particular session here to be used this. Now this option pen is basically when we have the scientific number that we are uh, disabling the scientific number. Now next what we have, the first details of the data, start date and date, then again using the get symbols which already we have discussed, we are downloading those data here. This then we have merged this data, this Nifty 50 and this Sensex here. So basic idea here is to examine the correlation or this spillover between the Nifty 50 and the BSE Sensex, because both those represent the same financial markets, only on register on the different platform. So the reasonably it is we should predict there should be a high correlation. So let us see how these two are moving. So once we downloaded the data, then we are preparing the data for the estimation. So what we have done, we have taken the returns and we have given the name of the Nifty 60. So this is the log return we have created, and now we will be using this particular data to estimate the GARCH models here. Now before that, let us plot those data and see here. Now if you observe here the plots, both these quite follows the similar pattern, and that is basically is expected because both these is representing the same economy, similar same financial market, only registered on the two different platform. So if you observe the similar phenomena we are observing in both these cases, so expectation is there should be high correlation among these, there should be high volatility spillover. So the descriptive statistics first we are finding. So these are the descriptive statistics we have, that is the variable number of observations, mean, standard deviation, median, trimmed, mean, absolute uh, deviation, minimum, maximum, range, skewness and kurtosis. Now we are calculating the correlation and covariance function here. So here basically we have 20-day rolling covariance, 100-day rolling correlation among these two. One interesting aspect what we are looking here, whenever there is the stable market, the correlation is almost, here we can see it is around 0 here. However, when there is the fluctuation in the market, the covariance has increased, and here it is correlation shows that it is almost similar remains. However, in this area what we have, the correlation goes a little bit less than 1, and it is increasing in here. So these are the area where basically we have the uncertainty. So in case of uncertainty we have the high correlation, and that's the basically theoretical. Financial theory says that if there will be more uncertainty, then the correlation will increase. When there will be calm period, the correlation may decrease, and that's we are observing here also. So once we plot that, what we are doing, first we have to do whether there is the arch effect is present or not. If you remember here in the previous classes when we have discussed about the arch model or the univariate GARCH model, so first thing we do that we test for the presence of arch effect. If there is the presence of arch effect, then only we can go to the using GARCH or arch models or its various extensions. Here similarly, to test that we use the multivariate arch test model, which is based on the package of MTS. So let us run here. Now if you see here, the null hypothesis of multivariate arch model is, the null hypothesis of is there is no arch effect, multivariate arch effect. alternate is there is R effect, and we have to take the decision whether this is equal to was 0 or this is equal to 1. If it is equal to 1, then we accept the null. If it is closer to 0, we basically reject the null, and here basically we accept the null. So if we reject the null, that means there is the presence of arch effect. So let us see the result here. So here we are able to find that in all cases, whether it's the test statistics or whether it's the rank based test, in both cases what we have, there is the presence of heteroscedasticity or arch effect. Why? Because the p value is closer to 0. So that means there is the quite reasonable plausible reason that we should go and use the volatility models. So the first volatility models what we have used the constant conditional GARCH model. Then in this case multivariate GARCH model, basically we have 3 steps. First step, what we do in the multivariate GARCH model, we follow the 3 steps. In the first step, we estimate the univariate GARCH model for univariate series. Then the step 2, we use this standard deviation here in the step 2 to fit the multivariate GARCH model. Now in R, to implement this, what basically we are doing, first we make the specification of univariate GARCH model. Then the second, we make multiple specification for the multivariate GARCH model. Then third, we use this specification to fit the model, or what we call to estimate the model. So let's what we are doing. So U spec is the name of the specification we are having. U GARCH specification is basically we are giving the univariate GARCH specification, which already we have discussed earlier, that it has the 2 component, mean model and the variance model. So the mean model here we are see 0 0, that means we are assuming only there is the mean. Variance model we are assuming the list GARCH 1 1 and the model is GARCH. Then that's the univariate GARCH specification we are doing. Now M spec, basically we are multiplying that same for the 2 variable. So M spec is the multi-spec replicate how many times? 2 times, because we have the 2 variables, comma U spec. This is the case. Now here we are using CC, constant conditional specification. What we are doing, C GARCH spec, M spec, where is equal to F. Basically this C GARCH is spec, this C GARCH spec from the RM GARCH package is for estimating copula GARCH model, multivariate GARCH model. However, if you are giving only GARCH specification, not any other specification, then this becomes equivalent to constant conditional multivariate GARCH model. So therefore we are using the GARCH spec. Otherwise the C GARCH is basically for the copula GARCH specification. So this we have done. Now we are using the GARCH fit. So here in RM GARCH package, what we have one for the specification, that is to specify the structure of the mean and variance equation. Second, we have command fit to basically estimate the models. So that's what we are having here. C GARCH specification, then C GARCH fit is basically to estimate the model. Then here, what is the specification? We have to give the reference, the C spec. So this is the specification I'm asking C GARCH to estimate, and the data is reference is given of this logarithm, and that model is stored into the GCC. So let us here estimate this. So it is being estimated, and here we have the result. So it has the copula GARCH fit. Remember here it will is basically for the copula GARCH fit, but for this our specific specification, this is equivalent to of constant conditional correlation GARCH. So we have to be careful that though it is appearing as the copula GARCH fit, but it is basically constant conditional correlation GARCH. Then here basically all the informations here we have, which is basically we have given. For example, distribution, multivariate normal distribution we have used. Number of parameters, it is estimated 8. So number of series is 2, number of observation was this, log likelihood function is this, average likelihood function this. Now these are the basically optimal parameters we have. These are the nifty. So this is the mean equation, and this is the omega, that means the variance constant for the variance equation. This is alpha 1, this is arch effect, beta 1 basically GARCH effect. Similarly for this Sensex, this is mu basically mean equation, omega constant of the variance equation, alpha 1 for the arch effect, beta 1 for the GARCH effect. And by looking from the probability value, we can say all these coefficients are significant. So this is the first indication that model is quite fit to the model. Then here we have the information criteria. Now, so as we have discussed in the beginning of this lecture, we will not discuss much about the constant. We will discuss in detail about the dynamic conditional correlation GARCH. So here we have the same process here we follow in the multivariate DCC GARCH also. So in the DCC GARCH also, what we will do, first we will get the univariate specification. Then we will multiply those specifications to be used for the multivariate GARCH model. Then third, then we will use this specification to estimate the model. Then we will see certain diagnostic test. Then we will use the forecast model. So now let us go here. So now in the first case GARCH 11 we are specifying. So let us first discuss. So here in the GARCH case, univariate GARCH specification we are giving, where the mean model is basically only mean. Variance model is GARCH 11. Distribution of the model is normal distribution we are assuming. Then the DCC specification, what we are giving, DCC specification, that is the same univariate GARCH specification replicated by 2 times for the 2 variable. DCC order we are giving 1 1, and the distribution is multivariate normal distribution we are estimating. So this is the basically DCC GARCH specification. Now this specification we are using here to fit the DCC model. So we are giving the reference to the specification and the data, then storing the result into the GDCC, and here if we write this, the results will be printed. So let us see here. So let us have this. Now if you see the result here, again DCC GARCH fit. So this will be the basic information of the model, and here we have the optimal parameters. This is again for the mean equation we have. This is the constant for the variance equation. This is the arch effect, and this captures the Garch effect. And these two joint parameters is for the DCC model we have. From this we can observe only in the nifty case the constant of the variance equation is not significant. All other coefficients are significant. So that means it seems the model may be reasonably fit here. Now, once you estimate the model, there are the certain information we have to know, and which is basically package dependent and the software dependent. So once we estimate what are the informations is being stored into the R, so that we can use those information. So for that, what we use slot names and the model. So if you give this, then here what we have slot names, that is there are the two types of slot is being created at the bank, MFIT and the model. And these two slots will store the two different kind of information. So what are the information we have stored into this MFIT model? So to use that, to know that, what we have names, GDCC MFIT. So here it stores the coefficient, matrix of coefficient, GARCH names, DCC names, coefficient variance, scores, conditional variance, scores, correlation matrix, covariance matrix. Here the correlation matrix, standard residuals, timer, Q bar, convergence. So all this information is being stored into the MFIT slot. Similarly, what are the stored into the model? So here in the model, what we have: model link, model description, data, fix, everything we have sigma being stored. So all those information you can extract. Now let us plot the GDCC. If you are using the plot GDCC here, it will ask, there are the 5 options we have for the plotting. That is conditional mean versus the realized returns. We can have conditional sigma versus the realized absolute returns, conditional covariance, conditional correlation. So let us see one by one. So let us place 1 here and hit the enter button. So here we have the option. So this is the conditional mean of the equations we have. What is the conditional mean over the years it is evolved. Now similarly we can plot the conditional sigma. So here we can see this is the nothing but the conditional sigma we have versus the returns. Now we can observe it is this conditional variance in the little dark line. It is quite closely able to capture the variation of the actual returns. So that means it seems quite fit. You can see here almost every turning point it is being able to capture here. So every turning point here we can see able to capture, and here you can see this way almost everywhere we are able to perfectly capture the movement. Now let us say the conditional covariance here. So this shows the conditional covariance. Again, if you observe that whenever we have the high fluctuation in the, if you remember the original data plot, it is able to capture those variations in the original data. So now last we can say the conditional correlation here. So again we can recall this is the conditional correlation, it is quite able to capture, and here we can observe it is always remains the either 1 and below that. So that means there is the quite strong movement between these two indices we have. Now the next we are going to use the forecast. So for the forecast we use the DCC forecast, then we give the estimated model name, how many observations ahead we wanted to forecast. So let us do the forecast here. Now using that forecast we can plot that. So let us say 0, now we are moved ahead. So let us estimate the forecast here. Now slot names, list names. Now let us plot the DCC forecast here. So using the forecast, we can, let us say, we will have the second, that is the covariance here. So here we have, this is the actual returns we have, and this is the forecasted value we have for 100. So there is the very minor fluctuations we have because the data is very little fluctuated. So this is the very minor fluctuations which is able to capture this in the DCC forecast we have. Similarly, we can uh, use the conditional covariance. So here again, this is the actual conditional covariance and this is the forecasted. So what we can observe, as time passes, conditional covariance is becoming more and more. So that means if you are investing in both this, the diversification chances is very limited to be for using these two indices assets here. Let us use the correlation here. So from this, what we can ultimately conclude? From this DCG GARCH model, where we use this to model the conditional variance between the Nifty 50 and the BSE Sensex, we are observing that there is quite a strong correlation between these two, and therefore we cannot use these two assets to diversify our portfolio. We we can use those assets for the diversify only when the returns are uh, different. So that's all for this lecture. See you in the next class. Thank you so much.